Hello engineers, welcome back. In the previous video, we learned about how to represent binary trees in arrays, right? So in this video, let's continue on that and we'll see what is a min heap and how that is represented in arrays and how we can do operations with it, okay? I hope you're ready. Let's get started. So in this video, we'll look at these topics. We'll first try to understand what is a full binary tree and what is a complete binary tree and what are the differences. And then we'll see how min heap can be constructed. We'll see how insert and remove can be performed in a min heap, and then we'll discuss time complexity of these operations, right? So let's first try to understand what is a full binary tree and a complete binary tree, okay? So I have this tree here. As you can see, if I go from top to bottom, at the first level we have a root node, and then root node can carry a maximum of 2 children, right? Left child and right child. And at this height, there are, of course, 2 children. And if I go down the tree, 2 has 2 children, 3 also has 2 children. So this tree is filled with maximum possible nodes, right? So what are the maximum possible nodes? Max nodes can be given as 2 to the power h plus 1 minus 1. So the height of this tree is 2, right? So we can plug it here. So 2 to the power 2 plus 1 minus 1. So this is 8 minus 1, which is 7. And we have 7 nodes in this tree, right? So if a tree is having all the possible nodes, if a binary tree is having all the possible nodes, it is called a full binary tree. So this is an example of a full binary tree, okay? Now I'm going to show you another example. So let's say I have this tree here. If we look at it, it does not have all the nodes that can be possible, right? So as we saw here, there are 7 possible maximum nodes that this tree can have of height 2. But as we can see, the number 3 is not having any left child or right child. So this is not a full binary tree, not a full binary tree. But if we look at it from top to bottom, and as we saw in the binary tree in arrays example, how do we represent a binary tree in arrays? We start filling it from left to right, right? So if we look at it from that perspective, the first node is filled, and at the next level, left child and right child are filled, and at the third level, left child and right child are filled, right? If a tree is following this kind of nature, where there are no gaps in the tree when it comes to filling, then this type of tree is called a complete binary tree, right? It is following the complete binary tree property. So what is not a complete binary tree? If we look at it from this tree, let's see this tree. This tree is also not having all the nodes. So this is not a full binary tree anyway, but is it a complete binary tree? So from left to right, if we start filling it, we can see gaps here, right? There is no left child of 2, there is no right child of 2, but other children of 3 and 5 are there. So this is not following a complete binary tree property. So this is not a complete binary tree, okay? So this is a clear distinction that we need to remember when building heaps. So the heap data structure will follow a complete binary tree. When we are building a heap data structure, we need to remember that it needs to follow the complete binary tree property, okay? Now let's see how we can build a heap. What is a heap and how we can build it? Let's say I have these numbers 5, 3, 8, 1. Let's say I want to build a minimum heap. So what is a minimum heap? Minimum heap is nothing but at the root, there will be the least element. Root will have minimum element, minimum value. Okay, that is the property we need to remember. So if a tree is having a minimum value amongst all the members, then it is called a min heap. And if there is a new member getting added, then we need to re-evaluate the tree and make sure that at the top there is only the minimum value available. Okay, so that is min heap. And when we remove, we will only remove from the top and readjust the tree so that the next minimum member will come to the top. Okay, so that is the property of a min heap data structure. So it is a binary tree, and specifically it is a complete binary tree, and it will follow the property that root will always have the minimum value. as opposed to maximum heap, which will have the property that root will always have the max value. It is just the opposite of min heap, right? So let's see how we can build this. So let's say I'm representing these in array. Okay, let's say this is my array, and let's try to insert it one step at a time so that we can understand insertion and removal processes as well. So let's start with insert. So let's say I want to insert 5. So let's say I want to insert 5. So since the heap is empty, there is nothing to do. I can directly insert 5, no problem. Now let's say I want to insert 3. For insert, we will always insert at the position which continues the complete binary tree property. So what is the rule for filling a complete binary tree? We always go one level at a time from left to right, right? So since we already have a root node, we need to go one level down and start filling it on the left side. If left is filled, we will go to the right side. And if both are filled, we will go one level down and start filling left to right. So that is the complete binary tree property, right? So we have inserted this. But is this following the minimum heap property? No, because what is the condition? Root will always have minimum value, right? So in order to make this tree a min heap tree, what do we need to do? The newly inserted element will need to be compared with its parent. Okay, so 3 is compared with its parent. If 3 is smaller than the parent, then they will be swapped. Okay, right now 3 is inserted here. Okay, and we compare with parent. We already know how to get parent value in our previous video. If you haven't watched that, please do watch it. So once we have the parent, we will compare it, and if it is smaller, then we will swap it. So once we swap it, the values will be like this. 3 will come here, 5 will go down. 3 will come here, 5 will go down. Now this is a min heap tree, okay? Because when we remove the element at the top, it will be the minimum value amongst the available values in the tree, okay? Now let's insert one more. Let's insert 8. We have finished 5, we finished 3. Now let's insert 8. So to insert 8, what is the property? It should follow the complete binary tree property. So we should insert from left to right. So since left is already full, we will insert it at the right position. Okay. After insert, we check with its parent. Is the parent smaller or is the newly inserted element smaller? In this case, the parent is smaller. So we will leave it. This is already in a min heap position. This is already a min heap. So nothing to do here. So 8 is inserted. Now let's insert 1. So how do we insert 1? So since this level is filled, we go down one more level and fill 1 here. Okay, and fill 1 here. Now again, the newly inserted element will be compared with its parent. So is 1 less than 5? Yes, so we swap it. But are we done? Is this a min heap? No. So we continue the process. So we still take the 1 and continue with its parent again until we reach the root node. So until we reach the root node, keep comparing with the parents. So we compare 1 with 3. 1 is smaller. So again, swap. So 1 goes here, 3 goes here. And this is the representation in the tree format. Okay. So we are making the alterations in the array itself. This is just a visual representation of that array, right? But we are making alterations in the array itself. We will do array swapping using indexes, right? So we are done with inserting. Now this is a min heap. Okay. So the process that we just saw, where we are inserting a new element and then we are continuously checking with the parent and keep swapping the newly inserted element until it reaches its right position. This process is called Heapify up. So the process which we just saw is called Heapify up. Okay. Now let's discuss how to remove elements. In a min heap or a max heap, the only element that we can remove is from the top. So we will have a method that will give us the root element basically. And that is the only element which we can remove from the heap data structure. Okay. So let's see how we can remove. So let's call remove method. Once we hit remove method, the first element will be removed. So what is the algorithm to remove it? We will find the rightmost value, or we will find the last value in the array and then swap it with the root element, right? So this is what we'll do. The lastmost element in the array is 5. So we will swap it with that. We will not swap it, we will just replace it with that. Okay, and then remove the last node. So now this is removed. Okay, now in our array the number 1 is removed, right? Now we need to check, is this a heap, min heap? Is this following the min heap property? The answer is no. So from the root we compare the children. While insert we were comparing the parents, while removing we will compare with the children, and then we will find a new place for this 5. Okay, let's compare. So we have 3 and 8 as the children. So we need to check what is the right place for 3. As you know, minimum number should come up, right? So which means that 5 should go down. So we will swap these two. Okay, and then once 5 is here, we will again compare with the children, if there are any children. If there are no children, our search will stop. Now is this a min heap? Yes, because the minimum element is at the top. So we have successfully removed the element 1. Okay, so we have removed once. Let's call remove again. To understand the process again, let's call remove. Now again, what should we do? We will take the last element in the array and use that value to replace the root node. So the number 3 is gone and it will be replaced with 8. And we will remove the last node. Okay, now again we check from the parent, from the root node, is this a min heap? We will compare with children. There is only left child. Is left child smaller? Yes, so we swap. So this is gone. Now these two are swapped. 5 goes up, 8 goes down, and visually we can see like this. Okay, is this a min heap now? Yes, so no problem. Third, let's call remove again. So what do we do? Same process. We will take the last element in the array and use that to replace the root. Okay, so one step is done. Now we will remove the last element. Second step. This is also gone. Now we will check, is this a min heap? Yes. So no children, so it is already a min heap. So we have successfully removed 3 elements in the heap and still retained the minimum heap structure as well as complete binary tree structure. Okay, so this process is called Heapify down. The process where we are removing one element, or basically we are pushing the root element to its correct position down the line, down to its correct depth. This process is called Heapify down. Okay, so while inserting we use the concept of Heapify up. In the remove method we have used the concept of Heapify down. Okay, now let's look at time complexity. So for insert, what happened when we were inserting? Let me draw the tree again. So let's say this was our tree, and if I want to insert something, I will insert using the complete binary tree property, and I compare with the parent. If the parent is smaller, nothing to do. If the parent is larger, then we swap with the parent and continue this process until we reach the root of the tree, right? So how many comparisons are being done? It depends on the height of the tree, right? So for every height we are doing a comparison. So the operation will become log n, O of log n, because the number of comparisons is dependent on the height. Similarly for remove, this is insert. For remove as well, we were doing one swap with the last element of the array, and then we were doing the comparison from the root, and we were pushing the element down until it reaches the correct position, right? Again we are doing log n operation here because the number of operations is dependent on the height. So in the worst case we get log n operation in both the cases. Okay, so that is the time complexity. So in this video, we have understood full and complete binary tree. We have seen the implementation of min heap in theory, and we have discussed the time complexity, right? In the next video, we will code all this in C++ and see how it looks like. Okay. So thank you so much for watching, guys. If you have any questions, definitely ask me. Do leave a like and comment if you have any questions or suggestions. Do subscribe to the channel and share it with your friends. Also bookmark the playlist. Thank you so much for watching. I will see you in the next one. Cheers.